Hello everyone. In this video, we will see the fundamental steps in digital image processing. This is the block diagram consisting of all the steps. First, you will be having the problem domain. You may have various problem domains. Now, the first step is image acquisition. Then you have filtering, image filtering and enhancement, image restoration, color image processing, wavelets, other image transforms, compression and watermarking, morphological processing, segmentation. You have feature extraction, image pattern classification and knowledge base. Now we will look at these steps one by one. First is the image acquisition. So here, this is the first step in digital image processing, which deals with the formation of the digital images via sampling and quantization from a physical scene. Now here, the purpose of an image acquisition is to convert the real world continuous image, that is the analog form, into the digital image, which can be stored, displayed and processed electronically. Now, here, this can be done by using the devices such as cameras, scanners or the sensors, and then converting it into a digital form so that it can be processed by a computer. Now, coming to the sampling, here actually we have two steps. One is the sampling and another is the quantization. First we will see what is sampling. Sampling, it is also called as the spatial discretization. That is meaning to say, sampling means it is dividing a continuous image into finite number of small elements called as pixels. Okay, that is, here it is a process of converting continuous image, which will be in analog form, that the image will be in analog, into a discrete image by dividing image into picture elements, that is into dividing it into a finite number of pixels. And here each pixel represents a specific location x comma y in the image. So you can define sampling as what? It is the process of measuring the amplitude of an image f of x comma y at discrete spatial coordinates x comma y. That is, it determines how many pixels will represent the image. Okay, and where each pixel is located. So here you have an example, that is the digital photograph. When when a camera captures a photo, the image sensors like the CCD or the CMOS chip, these will divide the scene into tiny picture elements which are called as pixels. Then each pixel will record the brightness or the color of that specific point in the scene, and these pixel values together form a digital image. Okay, so next is the importance of the sampling. So here the sampling, it will determine the image resolution, that is the number of pixels taken, which defines how detailed the image will be. And next is, it affects the image quality and the storage size. That is, high resolution images need more memory in order to store the pixel data. Then you have essential, that is, it is essential before the quantization, because you must first define the pixel positions. That is nothing but the sampling before assigning the intensity values, which is called as the quantization. Coming to quantization, it is also called as intensity discretization. That is, it is the process of converting the continuous range of intensity values into a finite number of discrete levels. Okay, so this range of intensity values, it is nothing but it can be gray level or it may be color values, and we have to convert it into a discrete levels, that is converting continuous bright values to a set of fixed digital intensity values. So here this quantization converts the continuous range of values into a finite set of discrete intensity levels. And here each pixel, that is after spatial sampling, each pixel has a continuous intensity, and this intensity, it is rounded off to the nearest available level in the digital system. Suppose you have like here it is given as the number of levels is equal to power of 2. It means that L is equal to 2 raised to k. If you have k is equal to 1, that it is, if it is 1 bit, then you will be having 2 raised to k levels. So 2 raised to 1, 2 levels, that is black and white. Or suppose here you have 8 bits, that is if value of k is 8 bit, 8, then it will be 2 raised to 8, that is 256 levels, which are gray levels. Then if you have a 24-bit image, then here you'll be having 2 raised to 24, that is nothing but 16.7 million colors, which will be a color image. Okay. And if f of x comma y is a scaled image, if f of x comma y is a scaled image, this one, f of x comma y, then the quantized image, that is fq of x comma y, it is given by this formula. Okay, that is it will represent each pixel with one of these discrete levels. Coming to the importance of the quantization, it will reduce the size, that is it will reduce the data size. If fewer intensity level means less memory is needed, and it determines the intensity resolution, that is more quantization levels allow smoother changes in the brightness or the colors, and fewer levels may cause banding or loss of details. So this was about the image acquisition. Next is image pre-processing or the enhancement. So here the goal of the image pre-processing or enhancement is to prepare an image for further processing or analyzing, such as for segmentation, recognition and classification. And this step, it removes the it improves the image quality, and it makes the contrast better by removing the noise, and it will make the features clearer and noise free. So here the techniques which can be used for image pre-processing or enhancement are contrast stretching, histogram equalization, you have smooth filter sharpening filters, and you have many more techniques. I have listed only a few here. Now the main purpose of the image pre-processing step is to make the image look better for human viewing, and to make it easier for the computers in order to analyze and extract the useful information. Now to enhance the contrast, remove noise, and highlight the important details. This is the purpose of the image pre-processing. Now here in image enhancement, like here it will make the image look better, it improves the contrast, it increases the visibility features, and it also it removes the noise. Then you have some intensity transformations like negative, log, power law. These all are the intensity transformations which will modify the intensity or the brightness of each pixel according to a function. Here this negative transformation, it will invert the pixel values, and log transformation, it will enhance the darker regions and it will compress the brighter regions. Similarly, you have power law, which is also called as the gamma transformation, which will adjust the overall brightness and the contrast depending on the value of gamma. Then you have special filtering, where you have smoothing filters which are used for noise removal. You have mean and Gaussian filter for that, and sharpening filters, that is for the edge enhancement. For that you have Laplacian filters and the high boost filters. And this special domain filtering, it is used for enhancement, where it is done directly on the image pixels. Next you have frequency domain filtering, where the enhancement is done using the mathematical transforms such as the Fourier transform and the homomorphic transform. Similarly, you have local contrast enhancement, where you will be using the methods like adaptive histogram equalization. So next step is image restoration. Now here in image restoration, it is the process of reconstructing or recovering an image which has been degraded by a known degradation model. Okay, that is here uh, like the image which will be degraded, that is nothing but it will be damaged, or it will be blurred, or it will be noisy. Why? Because due to known causes such as the camera motion, lens defects, or the environmental interference. And here, unlike the enhancement, which is sometimes subjective, this restoration, it strives for the objective recovery of the original scene. Here, meaning to say is image enhancement, it is about making an image look better to the human eye, which is the previous step which you have seen. There, it is done in order to look the image better for the human eye, and it's based on what looks good. So it can be subjective, that is different people may prefer different results. But on the other hand, image restoration, it tries to fix the images accurately in order to get back the original true picture, okay, because it was damaged. So it's objective because it uses mathematical methods in order to remove noise, blur, distortion, or some other defects in the image. So here the goal of the restoration is nothing but object recovery, that is to restore the image based on measurable quantitative criteria rather than subjective visual enhancement. So here this image restoration, it is these techniques are particularly useful when an image suffers from blur, noise, or the geometrical distortions. Geometrical distortions are nothing but these are caused by the lens curvature or the scanning errors. So some common techniques are inverse filtering, then you have Wiener filtering, then you have constrained least square. These all are the methods. There are many more methods. I have listed only 3 here. Next is the color image processing. So color image processing, it deals with the manipulation and analyzing of the color images, and it uses various color models like HSV, RGB, CMYK. There are many more color models in order to represent the color information and also to process the color information. So the colors may carry more information or some extra information than the grayscale images, because each pixel, it has 3 or more color components, that is the red, green, and blue, and this helps in better object detection, recognition, and the analysis. The challenges here are there may be different color models, there may be different color conversions, that is converting between color spaces can cause the data loss or distortion, and you may have pseudo color, that is assigning artificial colors to the grayscale images in order to highlight the features which are used in medical or satellite imaging. Then here this color image processing, it will improve the segmentation, recognition, and also the detection of the features. Segmentation, like separating the objects based on their color differences. Recognition, identifying the objects or patterns using the color cues. And feature detection is detecting the edges, points, or boundaries more accurately using the color contrast. So some of the techniques which are used are color space conversion, then pseudo color mapping, color transformation, and color segmentation. Next, you have multi-resolution processing and wavelets. So here this multi-resolution processing, it deals with the representation and the analysis, that is analyzing an image at multiple levels of resolutions or scales. That is, it helps in understanding both the fine details and the global structures within an image. So here images contain features at different levels, that is at the edges, textures, shapes, etc. And analyzing an image at only one resolution may hide the important details. Therefore, the multi-resolution method break down the image into several resolution levels in order to analyze fine and coarse details separately. So here it will allows the efficient representation, compression, feature detection. This compression, it will reduces the data size without much loss of quality, and feature detection, it will identify the edges, textures and the patterns. And these are useful for texture analysis, image fusion and the compression. So some of the common techniques which are used are Gaussian or Laplacian pyramids, wavelet transformation, multi-resolution texture analysis. Next step is the image compression. So here in image compression, this is the process of reducing the amount of data uh, which is required to represent an image without significantly affecting its visual quality. Okay, so the visual quality should not be degraded. In such a way, we have to reduce the amount of data which is used to represent the image, and it is efficient for like it is essential for efficient storage and transmission of image data, and because it helps in reducing the bandwidth, usage, memory requirements and the power consumptions. Now here it distinguishes between the lossy and the lossless compression. So lossless compression, it is nothing but where the original image can be perfectly reconstructed from the compressed data, and it is used in applications where the accuracy is critical, such as medical or scientific imaging. And lossy compression, here some information is lost during the compression in order to achieve higher compression ratios. So the decompressed image, here it will be an approximation of the original image but visually similar. These are some of the common techniques: lossless, run length, Huffman coding, arithmetic coding. Then you have lossy, like lossless compression methods are run length coding, Huffman coding, arithmetic coding, and lossy compression techniques are transform and wavelength coding. Okay. Next you have the morphological processing. So here it is concerned with the tools for extracting the image components that are useful in the representation and the description of the description of the region or the shape. And here this works on the shape of the objects in binary or the grayscale images, and it is a powerful for boundary extraction, object connectivity and the skeletization, and it bridges the image enhancement or the processing and the higher level segmentation techniques. And some of the common techniques which are used here are structuring element operations such as dilation, erosion, opening, closing, hit or miss transformation, and region based morphological operations. So in general this morphological processing, it uses the shape based operations in order to extract the meaningful structures from the images and making it powerful link between the image enhancement and the segmentation. Next step is the image segmentation. So image segmentation, it is the process of partitioning a digital image into multiple meaningful regions. That is, it will help to identify and isolate objects and their boundaries. That is nothing but the lines, curves or edges within an image. And here it delineates the objects from the background. That is, it will separate the objects from the background in order to locate and outline the important structures or the objects. And it will convert the images into some meaningful analyzable regions for further processing or the interpretation. So these are some of the common techniques which are used for image segmentation, like thresholding, region-based, edge-based segmentation, graph cut, clustering methods. Next you have representation and description. Next step is the representation and the description. So here the representation and description, it will follow the output of the segmentation stage. That is, this representation here, it deals with how the region is described, that is boundary region. And it defines how the extracted region's shape, boundary or area will be stored for further analysis. And regarding description, here it deals with the extracting of quantitative information like shape, then you have texture. Okay, and these features will help in classification, recognition and interpretation of the objects. These are some of the common techniques which are used in the representation and description stage. Then you have object detection and the image analysis. So here in object detection, this is the fundamental step. Sorry, this is the final fundamental step where it is a process of assigning a label to a object which has been recognized. So at this stage, the system will interpret the scene and it will identify the object. So object detection and the image analysis, these are the higher level processing in the computer vision that will aim to identify, label and interpret the objects or the regions within an image. And these techniques, these are helpful in order to understand the scene and make informed decisions or predictions based on the visual data. And here the goal is to assign the labels to the objects to interpret the visual scene, and the output can be a label, decision or the model which represents the scene structure. And these are some of the common techniques which are used for object detection and the image analysis. Then the last one, which is connected to all the steps, it is nothing but the knowledge. That is knowledge about the problem domain, which plays a crucial role or the important role in guiding and controlling various processing operations. And here it provides the system with context and helps it make the intelligent decisions during the image analysis. Now this this knowledge, it can be complex or it may be simple. Now simple knowledge, here it will contain the basic information about the image, such as the detailing regions, information of interest to be located, but it will limit the search. Okay, that is one of the disadvantage of the simple knowledge. Whereas the complex knowledge, here it involves the detailed domain specific, and this is often domain specific information, and often it is stored in the database. For example, you will be having a satellite image database containing high resolution maps which can be used for land use classification, crop or forest monitoring and so on. So this knowledge, it is used to control and coordinate multiple processing modules. So here it will guide the operation of each processing module, and that is nothing but the enhancement, segmentation, classification. So it will guide the operation of each processing modules, which we have seen in the starting of this video in the block diagram. And also it will control the interaction between the modules in order to ensure the correct processing flow. So this was about the fundamental steps in the digital image processing. Hope you have enjoyed the video. Thank you.